Welcome to the BrainOmega channel. In today's session, we're diving into a crucial topic in the world of artificial intelligence. The main goal of this tutorial is to take a significant step forward toward understanding and implementing LLM alignment within our community. So, what exactly do we mean when we talk about alignment in large language models? At its core, alignment isn't just about making an AI smarter, it's about making it wiser and more responsible. As you can see on the slide, alignment is the dedicated process of training and fine-tuning an LLM so that its actions and responses are consistently in sync with human values and intentions. The ultimate objective is to sculpt these powerful models into partners that are not only helpful but also fundamentally safe to interact with. The diagram on the right beautifully illustrates this. It's a continuous cycle. We provide feedback, which helps refine the large language model. This refinement leads to what we call aligned positive outcomes, outputs that are beneficial and in line with our expectations. This process is repeated, creating a constant loop of improvement. To achieve this, the entire concept of alignment is built upon three foundational pillars, being helpful, honest, and harmless. First, helpful. This means the AI must go beyond just processing words. It needs to accurately grasp the user's true goal and genuinely attempt to meet that need. It's about being a useful and effective tool. Second, honest. An aligned LLM must be a source of truth. It should provide factually correct information and crucially have the integrity to admit when it doesn't know something, rather than fabricating an answer. This pillar is all about building trust. And third, harmless. This is the ethical safeguard. The model must be explicitly designed to steer clear of generating content that is dangerous, biased, unethical, or otherwise harmful. It's our commitment to ensuring AI contributes positively to the world. By focusing on these three pillars, we can guide the development of large language models that are not just powerful, but also principled and beneficial for everyone. For those of you who want to dive deeper, the source code of this tutorial and the project is accessible in our GitHub repository. You can have access to the link in the description of this video. Now that we understand what alignment is, let's explore what it gives us and what its limitations are. This slide tackles a crucial distinction. Alignment is a powerful path toward building trust in AI, but it's not a magic bullet for achieving full explainability. First, let's focus on the strong link between alignment and trustworthiness. Think about anyone or anything you trust in your daily life. Perhaps a skilled pilot or a seasoned doctor. You trust them because their actions are reliable, predictable, and consistently lead to positive outcomes. It's the exact same principle with LLMs. By meticulously aligning a model to be helpful, honest, and harmless, we ensure its behavior is consistent and acts in the user's best interest. As the Venn diagram illustrates, an aligned LLM and a trustworthy LLM are deeply interconnected concepts. Alignment is the how, trustworthiness is the result. However, the story changes when we compare alignment to explainability. Here, the link is much weaker, and this is a critical concept to grasp. Alignment is primarily concerned with the output, the what. It asks, is the model's final answer correct, safe, and useful? We are validating the quality and safety of the end product. Explainability, on the other hand, digs into the process, the why. It seeks to answer how exactly did the model navigate its billions of parameters to generate that specific output. This brings us to the black box dilemma, perfectly shown in the second diagram. We can have a model that is perfectly aligned. It gives us a validated, correct, and safe output every time. Yet the internal decision-making process that produced it can remain opaque. We can confirm what it concluded, but we can't always trace the precise path of why. So, the key takeaway is this. Alignment is our most effective tool for creating reliable, predictable, and safe AI that we can fundamentally trust. It solves the problem of behavior. But we should see it as distinct from the separate, ongoing scientific challenge of making these incredibly complex systems completely transparent. So, where is the field of alignment heading? This slide gives us a glimpse into the future, moving beyond the basics to explore the core philosophies and advanced techniques that are defining the next generation of AI. As the diagram illustrates, the path forward involves integrating three powerful and sophisticated approaches to build a more deeply and reliably aligned AI. Let's look at each of these pillars. First, we have AI-driven preference labeling. One of the biggest challenges in alignment is the sheer scale of human feedback required. It's incredibly time-consuming and costly. This technique is the solution. We are essentially training one AI model to understand human values and preferences so well that it can automate the process of labeling data for other models. Think of it as creating an AI supervisor that can apply human-like judgment at machine speed, breaking the bottleneck of manual work. Next, we have constitutional methods. This is a profound shift in philosophy. Instead of just telling an AI what not to do from the outside, we embed a set of core principles, a constitution, directly within its own operational logic. This gives the AI a framework for self-correction. It can review its own response, check it against principles like be helpful and harmless, and then revise it before it ever reaches the user. It's about building models with an internal moral compass. Finally, let's talk about advanced reasoning curricula. This is about teaching an AI how to think, not just what to know. Rather than just exposing a model to vast amounts of data, we create a structured training program, much like a school curriculum for a person. This curriculum is specifically designed to enhance the AI's ability to perform complex, multi-step reasoning and to follow a logical chain of thought. It's the difference between memorizing facts and developing true critical thinking skills. Ultimately, these three frontiers are converging. By automating feedback at scale, instilling principles for self-governance, and actively teaching complex reasoning, we are building the foundation for AI that is more capable, robust, and fundamentally aligned with human values. So, how do we actually implement alignment? Let's dive into the most common and effective method used today, RLHF, which stands for Reinforcement Learning from Human Feedback. As the diagram here illustrates, it's a dynamic, multi-stage process that creates a powerful feedback loop between human trainers and the AI model. The entire process begins with Step 1, Supervised Fine-Tuning or SFT. Think of this as the model's foundational education. We take a massive pre-trained model and give it its first taste of what we want it to be. We do this by training it on a high-quality human-crafted dataset of ideal conversations. This is like giving a student a textbook filled with perfect examples to learn from. This initial step teaches the model the basic style, tone, and safety protocols we expect. Step 2 is about building a judge. This is where we train the reward model. We take our model from the first step and have it generate several different responses to a variety of prompts. Then, human reviewers look at these responses and rank them from best to worst. This data, this collection of human preferences, is then used to train a completely separate model. The sole purpose of this reward model is to learn to predict which kinds of answers humans will prefer. It becomes an automated judge of quality. Finally, we reach Step 3, Reinforcement Learning Optimization. This is the most dynamic phase. The main LLM now operates in a live training environment. It generates a response, and our reward model, the AI judge we just built, immediately gives that response a score. This score acts as a reward signal in a reinforcement learning loop. Using a common algorithm like PPO, the model continuously adjusts its own internal strategy to try and maximize the rewards it gets from the judge. It's essentially a cycle of trial and error at a massive scale, where the model learns to consistently produce outputs that it knows will be scored highly by the human-calibrated reward model. So, in short, we first show it what good looks like, then we build a judge that understands our preferences, and finally, the model practices in front of that judge to perfect its behavior. This sophisticated three-step process is the engine behind today's most capable and aligned LLMs. Imagine you're a music producer trying to get the perfect vocal take. The old way is complicated. You first hire a panel of music critics to write a detailed scoring rubric for what good singing is. Then you use that complex rubric to coach the singer, take by take. It's slow, expensive, and often unstable. What if you could just sit with the singer, play them two different melodies, and say, "I prefer this one"? You just provide a simple preference. The singer learns directly from your choice, gradually steering their performance toward what you like. That, in a nutshell, is the breakthrough of direct preference optimization, or DPO. It's a powerful and elegant technique that scraps the complex machinery of traditional methods and teaches language models to be more helpful, safe, and aligned directly from simple human or AI feedback. Before DPO, the gold standard was reinforcement learning from human feedback, or RLHF. As the name suggests, it's a multi-stage process. First, you train a separate reward model. You show it thousands of pairs of model responses and ask humans which one they prefer. The reward model learns to predict which response will get a higher score. Second, you use that reward model as a judge in a complex reinforcement learning loop. Your language model generates text, the reward model scores it, and you use algorithms like PPO to nudge the language model's policy toward generating higher scoring text. This process works, but it's a beast to manage. It involves training two massive models. It's computationally expensive because you're constantly sampling from the policy, and it's notoriously unstable and sensitive to hyperparameters. DPO's authors asked a brilliant question. Can we skip the separate reward model and the RL loop entirely? Their key insight was this: your language model is secretly a reward model. Through a clever mathematical derivation, they showed that any optimal policy trained with RLHF has a direct fixed relationship with its underlying reward function. This means you can rephrase the entire optimization problem. Instead of training a reward model and then training a policy to match it, DPO defines the loss directly in terms of the policy itself. It collapses two complex stages into one simple, stable step. So, how does it do this? Let's look at the DPO loss function. It might look intimidating, but the idea is incredibly intuitive. For every training example, you have a prompt, a preferred response, Y sub W, and a rejected response, Y sub L. The DPO objective is to maximize the likelihood of the preferred responses over the rejected ones. Let's break it down. The core idea. At its heart, it looks at the log probabilities your model, pi theta, assigns to the winning and losing responses. The goal is to make the winner's probability go up and the loser's go down. The reference model, pi ref. You don't want the model to stray too far from its original stable knowledge base. The reference model, usually your initial supervised fine-tuned SFT model, acts as an anchor. DPO penalizes the policy for deviating too much from this reference, which prevents the model from forgetting its core capabilities or collapsing into repetitive outputs. The beta hyperparameter. This is your main tuning knob. It controls the strength of that anchor. A low beta keeps the model very close to the reference policy, leading to more conservative updates. A high beta allows the model to chase the preferences more aggressively, but risks instability. Think of it as the stretchiness of a leash. The sigmoid weight. This is the most elegant part. The entire term is wrapped in a logistic sigmoid function. This acts as a dynamic, intelligent weight. When the model already assigns a much higher probability to the winning response than the losing one, this weight is small. But when the model is wrong, when it thinks the losing response is better, the weight becomes large. This forces the model to focus its learning effort on the examples it's getting wrong, making training incredibly efficient and stable. In short, DPO increases the relative log probability of preferred responses, weighted by how incorrectly the model currently ranks them. The beauty of DPO is its simplicity. The practical pipeline is just 2 steps. Data collection. Start with a supervised fine-tuned SFT model. For a set of prompts, generate 2 responses. Have a human labeler or a more powerful AI. Choose the preferred one. This creates your preference dataset. If you're using a public dataset, this is already done for you. Fine-tuning. Optimize your SFT model using the DPO loss function. That's it. No separate reward model, no complex RL sampling loops. The paper even provides a PyTorch implementation that's just a handful of lines long. And if you don't have an SFT model to start with, the paper suggests a simple hack. Just fine-tune a base model on only the winning responses from your preference dataset to create a proxy SFT model before you begin DPO. So, does it work? The paper's experiments show a resounding yes. More efficient. On a controlled sentiment generation task, DPO achieved a better reward KL trade-off than PPO, even when PPO had access to the true ground truth reward function. This means for any given level of deviation from the original model, DPO gets you a higher reward. Higher quality. In summarization and single-turn dialogue, DPO consistently matched or outperformed strong RLHF baselines. For instance, in summarization, DPO achieved a 61% win rate against reference summaries, beating PPO's best performance of 57%. It was also the only computationally feasible method that significantly improved upon the chosen responses in the Anthropic dialogue dataset. More stable. The approach is far less sensitive to hyperparameters and sampling temperature than PPO, which can see its performance collapse under different settings. Direct Preference Optimization, or DPO, is a revolutionary, more direct approach, and today we're going to implement it from scratch to fine-tune the powerful LLaMA-3 model. In this video, we'll cover the entire pipeline. We have already explained the theory of DPO, so we'll dive into the code using cutting-edge libraries like Hugging Face TRL and PEFT. We'll use techniques like LoRA for memory-efficient training and quantization to make this all possible on consumer-grade hardware. This is a complete end-to-end guide. By the end, you'll have a deep, practical understanding of how to take a powerful base model and align it with your own data and preferences. Let's get started. Before we jump into the code, let's quickly understand the 3 core technologies that make this project possible. First, Direct Preference Optimization, or DPO. Traditionally, to align a model with human preferences, a complex process called reinforcement learning with human feedback, or RLHF, was used. DPO is a newer, more elegant solution. It works with a simple but powerful type of data set, one that contains a prompt, a chosen or preferred response, and a rejected or less preferred response. The DPO loss function then directly optimizes the model to make the chosen responses more likely and the rejected responses less likely. It's more stable and often more effective than RLHF. Second, parameter-efficient fine-tuning, or PEFT, using a technique called LoRA. Fine-tuning a model with billions of parameters would require a massive amount of GPU memory because you need to store the gradients and optimizer states for every single weight. LoRA is a brilliant solution. we freeze the entire pre-trained model. All its billions of weights remain untouched. Then we inject tiny trainable matrices, called LoRA adapters, into the model's layers. We only train these small adapters, which represent a tiny fraction of the total parameters. This dramatically reduces the memory requirements, making fine-tuning possible on a single consumer GPU. Third, quantization. Even just loading a model like LLaMA-3 8B can take over 16 gigabytes of VRAM. To solve this, we use quantization. We load the model's weights using 8-bit integers instead of the standard 32-bit or 16-bit floating point numbers. This can cut the memory needed to load the model by 50 to 75%, making it feasible to run on more accessible hardware. By combining these three techniques, DPO for effective alignment, LoRA for memory-efficient training, and quantization for accessible model loading, we create a powerful and practical fine-tuning pipeline. So, you want to run this powerful AI model, but maybe your computer isn't quite up to the task? Don't worry at all. We can easily run this in the cloud using Google Colab Pro. The very first thing we need to do is give our project some serious power. Let's go up to the Runtime menu and click on Change Runtime Type. You'll see a pop-up window. The magic happens in the hardware accelerator. Instead of the standard GPU, if you have Colab Pro, you can select the powerful 800 GPU. This is a game changer for speed and will make running this model a breeze. Okay, with our 800 selected, let's get the software ready. We'll run our pip install commands to load all the essential Python libraries for this project. Next up, let's grab the code itself. We'll use a quick git clone command to download the entire project from GitHub. And just like that, we're ready to go. We'll move into the new folder and run the main script. And there it is. The model is running and generating its answer to our prompt. It's that simple to get started, even without your own powerful hardware. Let's start our code journey with dataprocessing.py. This script has one simple but crucial job: to prepare our dataset for the DPOTrainer. The DPOTrainer, which we'll see later, requires each example in our dataset to be a dictionary containing 3 specific keys: prompt, chosen, and rejected. Our format example function does exactly this. Let's walk through it. It takes a single example from our raw dataset and the tokenizer. First, it constructs the messages list that represents the start of the conversation. It checks if the example has a system prompt, and if so, adds it. Then it adds the user's question. Second, it uses a very handy function, tokenizer.applyChatTemplate. Every chat model has a specific format it was trained on, with special tokens to denote the start and end of turns. This function takes our list of messages and correctly formats it into a single string, prompt, complete with all the necessary special tokens. We set add generation prompt equals true to ensure it adds the token that signals to the model that it's the assistant's turn to speak. Third, it takes the chosen and rejected responses from the dataset and appends the tokenizer's end of sentence token to each one. This signals the end of a complete generation. Finally, it returns a dictionary with our 3 required keys, perfectly formatted for our DPOTrainer. This function will be applied to every single example in our dataset. Now let's move to the main event, training.py. This script orchestrates the entire fine-tuning process. We start by importing all the necessary libraries. We have Torch for our core deep learning framework, datasets and transformers from Hugging Face for loading our data and models, PEFT for our parameter-efficient fine-tuning, and TRL, which contains our DPOTrainer. Inside our train model function, the first step is to set up our tokenizer. We load it from the Hugging Face hub using autotokenizer.from pre-trained, pointing it to our base model. Then we configure it. We set the pet token to be the same as the EOS token, end of sentence token. This is a common practice for autoregressive models. We also set padding side equals left. This is a subtle but very important detail for causal language models. It ensures that when we batch multiple sequences of different lengths together, the padding is added to the left side so the final unpadded token of every sequence aligns on the right. This is crucial for efficient next token prediction. Finally, we explicitly define a chat template. While many models have this built in, setting it ourselves ensures maximum compatibility. This template uses a Jinja-like syntax to define exactly how a list of messages should be formatted into a string, using special tokens like imstart and imend to delineate turns. This guarantees our input is formatted perfectly. With our tokenizer ready, the next step is to load our data and our base model. First, we use load dataset from the datasets library to download our preference dataset directly from the Hugging Face hub. We're using the Intel Orca DPO pairs dataset, which is perfect for this task. Then, we use the .map method to apply our format example function to every single example in the dataset. This transforms our raw dataset into the prompt, chosen, rejected format that the DPOTrainer needs. Next, we load our base model, Unsloth LLaMA-3 8B. This is a special version of LLaMA-3 optimized for faster training. Let's look at the arguments to from pre-trained. Device Map Auto is a fantastic feature that will automatically distribute the model's layers across multiple GPUs if you have them, or load it onto a single GPU or the CPU. We also specify torch D-type torch B-float 16. This enables mixed precision training, which uses a more efficient data type for calculations, speeding up training and reducing memory usage. Finally, and this is a critical step for combining quantization with LoRA, we call prepare model for K-bit-A training. This function from the PEFT library does some important housekeeping under the hood, like correctly casting certain layers to ensure that gradients can flow properly through a quantized model during training. This makes our efficient fine-tuning possible. Okay, we have our massive LLaMA-3 model loaded in memory, but it's frozen. We're not going to train its original weights. Instead, we're going to use the LoRA technique. First, we define our LoRA config. This object holds all the settings for our LoRA adapters. Let's break down the key parameters. R is the rank of the LoRA matrices. This is the most important hyperparameter. A smaller R, like 8 or 16, means smaller adapter matrices and fewer trainable parameters, leading to faster training but potentially less expressive power. A larger R, like 64, gives the model more capacity to learn, but increases the memory requirements. LoRA alpha is a scaling factor that is often set to be the same as R, and LoRA dropout applies dropout regularization specifically to the LoRA layers to help prevent overfitting. Once we have our configuration object, we call the magic function getPEFTModel. This function takes our base model and the LoRA NICFG and it goes through the model's architecture, finds the target layers, usually the attention layers, and injects our small trainable LoRA adapter matrices next to them. It also handles freezing all the original weights. After this line, our model object is now a PEFT model, ready for efficient training. Now we're at the final setup step before training, configuring the DPOTrainer. This is a fantastic high-level trainer class from the Hugging Face TRL or Transformer Reinforcement Learning Library. It abstracts away all the complex math of the DPO loss function. First, we create a DPO config object. This holds all the training hyperparameters. Let's highlight a couple of key ones. Gradient accumulation steps is a crucial technique for training with small batch sizes. It allows us to compute gradients over several small batches and only update the model weights once, effectively simulating a much larger batch size without using more memory. Gradient checkpointing is another memory-saving trick that trades a little bit of extra computation time for a significant reduction in memory usage. We also set our learning rate, scheduler, and other standard training parameters here. Once our config object is ready, we instantiate the DPO-Trainer. We pass it our LoRA adapted model, our DPO-ish CFG, our processed dataset, and our tokenizer. One very cool feature of the DPO-Trainer is that we can set ref model equals none. In DPO, you need a reference copy of the original frozen model to calculate the loss. By setting this to none, the trainer is smart enough to automatically create and manage this reference copy for us, which simplifies our code a lot. After all that careful setup, the actual training process is beautifully simple, thanks to the Hugging Face Trainer API. We simply call trainer.train. This one line kicks off the entire fine-tuning process. The trainer will handle the training loop, moving data to the GPU, calculating the DPO loss, performing backpropagation, updating the LoRA weights with the optimizer, and adjusting the learning rate with the scheduler. It will also handle all the logging and progress bars for us. It's an incredibly powerful abstraction. Once the training is complete, we need to save our work. We call model.save pre-trained open parenthesis output directory close parenthesis. Because our model is a PEFT model, this command is smart. It knows not to save the entire multi-billion parameter LLaMA model. Instead, it only saves the tiny LoRA adapter weights that we actually trained. This is why our final output directory will be very small, maybe only a few megabytes instead of many gigabytes. We also save the tokenizer to the same directory. This is good practice as it bundles the exact tokenizer configuration with the trained adapters, making it easy to load everything together for inference later. Now that we've fine-tuned our model, let's see how to use it in Inference.pe. The load model for chat function handles getting our model ready for a conversation. First, we load our tokenizer from the base model and configure it with the exact same chat template and padding settings we used during training. This consistency is crucial. Next comes the model loading, which is a two-step process. First, we load the original massive frozen base model, just like we did before training. Second, we use PEFT model from pre-trained. This function takes the base model and the path to our saved adapter path directory, and it loads our small, fine-tuned LoRA weights and merges them into the base model's architecture. We now have a single model object that has the full power of a Llama-3 combined with the specific alignment we taught it during DPO training. Finally, we switch the model into evaluation mode with model.eval. This turns off things like dropout. We also set use_cache equals true, which is an optimization that allows the model to reuse computations for past tokens, significantly speeding up the generation of long responses. With our model loaded, the chat function handles the process of generating a single response. First, just like in our data processing step, we use tokenizer apply chat template to format our system message and user message into a single, correctly formatted prompt string. Next, we use a very convenient high-level tool from the Transformers library, the pipeline. A pipeline abstracts away a lot of the manual tokenization and decoding steps. We create a text generation pipeline and give it our fine-tuned model and tokenizer. Finally, we call our generator with the prompt. We pass in several parameters to control the generation process. DoSample equals true tells the model to use sampling instead of just greedily picking the most likely next token, which makes the output more creative. Temperature controls the randomness. A higher value means more random. A lower value means more deterministic. And TopWP enables nucleus sampling, another advanced sampling technique. The pipeline handles the rest, and we simply return the generated text from the output. Finally, we have main.py, our project's entry point. This script serves as a command line interface, or CLI, that lets us control our entire application from the terminal. We use Python's built-in argparse library to do this. First, we create our parser. Then we add all the arguments we want to be able to control. The most important one is mode, which is a required choice between train and chat. This single argument will determine what our script does. We also add arguments for things like the base model name, the dataset, and the user message for chat mode. After parsing the arguments provided by the user on the command line, we have a simple if-else block that acts as a router. If the user ran the script with --mode train, we call our train model function from training.py, passing in the relevant arguments to start the fine-tuning process. If the user ran it with --mode chat, we call our load model for chat and chat functions from Inference, passing in the user's message to generate and print a response. This simple, clean structure allows us to manage both training and inference from a single, easy-to-use command. So let's take a moment to recap the powerful and modern fine-tuning pipeline we've just built. We've gone deep into direct preference optimization, learning how to use preference pairs to effectively align a language model. We've mastered an incredibly efficient workflow using quantization to load a massive model into memory and then using PEFT with LoRA to fine-tune it with minimal resources. We've structured this all into a complete application with clean, modular code for data processing, training, and inference. And finally, we've tied it all together with a flexible command line interface. You now have the knowledge and the code to fine-tune state-of-the-art language models on your own custom data. I highly encourage you to experiment. Find a different preference dataset on the Hugging Face hub and try training with it. Tweak the LoRA rank R and see how it affects the model's performance. As a great next step, you could even take the inference PyScript and wrap it in a Gradio UI to create a shareable web demo of your custom-tuned model. Thank you so much for joining me on this deep dive. If you learned something valuable today, please give the video a like and subscribe for more tutorials on cutting-edge AI techniques. Happy fine-tuning! Hello, everyone, and welcome back to the BrainOmega channel. Today, we have another tutorial and hands-on session for you, and we're tackling one of the most critical topics in artificial intelligence, LLM alignment. We'll explore exactly how developers take a powerful but raw AI and carefully shape it to be helpful, honest, and safe for users. Have you ever stopped to think about the magic behind an AI like ChatGPT? You ask it a complex question, and it doesn't just spew out random text from the internet. It understands your intent. It adopts the right tone. It tries to be helpful. How did a machine learn to be so cooperative? The journey from a raw, chaotic language model to a helpful assistant is not an accident. It's the result of a deliberate and ingenious process called alignment. Today, we're taking a deep dive into this process. Using this seminal diagram from OpenAI's research on InstructGPT, the model that paved the way for ChatGPT, we'll explore the science of teaching an AI to share our goals. We will break down each step in detail, understand why alignment is arguably the most important problem in AI safety, and examine the significant challenges that still have researchers racing to find better solutions. This is the story of how we're trying to make sure AI works for us, not just near us. Let's get started. Imagine a brilliant student who has read every book in the library. They have all the knowledge, but they're unfocused, they ramble, and they don't know how to answer a direct question. That's a base language model like the original GPT-3. Its only training was to predict the next word on a massive scale. The alignment process is how you turn that brilliant but unfocused student into a dedicated, helpful research assistant. The core technique is reinforcement learning from human feedback, or RLHF, and it begins with step 1, supervised fine-tuning SFT. The goal here is to give the model a basic template for what a good answer looks like. The process starts with collecting real-world prompts, many of which came from actual users of OpenAI's early API. This is crucial. It's not just academic questions, but messy, real-life requests. For our example, the prompt is, explain the moon landing to a 6-year-old. Instead of letting the AI try to answer, a human expert, a labeler, steps in and writes a high-quality exemplary response. You see it here. Some people went to the moon. This is called demonstration data because it demonstrates the desired behavior. This curated data set containing thousands of these prompt demonstration pairs is then used to fine-tune the base model. Think of it like a chef's training. You don't just give them a cookbook, you show them videos of a master chef preparing each dish perfectly. They learn the right techniques, the right timing, and the right presentation. This step alone provides a massive improvement, but SFT has a weakness. You can't possibly create a human demonstration for every single type of question a user might ask. To get an AI that can generalize to new, unseen prompts, we need to move from learning by imitation to learning from preference. That brings us to step 2, training a reward model. This is where we build our AI judge. The objective here is to teach a separate AI to understand human preferences with nuance. We start with a prompt and have our SFT model from step 1 generate several different answers. Here, A, B, C, and D. Let's imagine what these could be. Answer A might be technically correct, but full of jargon about orbital mechanics. Answer B might be factually wrong, saying they flew there in a balloon. Answer C might be simple, accurate, and engaging for a child. Answer D might be a bit too simplistic, leaving out key details. A human labeler then ranks these outputs. It's often much easier for a person to compare and say, C is better than A, which is better than D, which is better than B, than it is to write the perfect answer C from scratch. This ranking, D is preferred over C, which is preferred over A, and so on, is the crucial piece of data. Thousands upon thousands of these comparisons are collected and used to train a completely separate model, the reward model, RM. This reward model becomes our automated judge. It doesn't know how to write a story about frogs itself, but after reviewing countless ranked examples, it develops an incredibly sophisticated sense of what humans find helpful, truthful, and well-written. It learns to assign a high score to good answers and a low score to bad ones. Now that we have our judge, we can use it to train our main AI at a massive scale. And this leads to the grand finale, step 3, reinforcement learning. This is where the magic truly happens, in a dynamic and continuous loop. A new prompt is sampled, like write a story about frogs. Our main AI, the policy, writes an answer. Instantly, the reward model we just trained swings into action. It reads the prompt and the AI's story and outputs a single number, a reward score. A high score says, great job. A low score says, try again. This reward is then used to update the AI's policy using an algorithm called PPO, or Proximal Policy Optimization. In simple terms, PPO is a clever way of taking a small, stable step in the right direction. It encourages the model to try things that will get a higher reward, but it does so cautiously, ensuring the model doesn't drastically change its strategy and forget all the useful language skills it already has. This loop runs millions of times. Generate, score, update, generate, score, update. The AI is essentially in a high-speed training simulation, constantly refining its ability to produce outputs that our AI judge and, by extension, humans will like. However, this intense optimization comes with a risk mentioned in the article, the alignment tax. If you only train the AI on pleasing the reward model for user tasks, it can start to forget some of its core knowledge and perform worse on other academic benchmarks. To solve this, OpenAI mixes a small amount of its original pre-training data back into this step. It's like making a student study for a specific exam, but also ensuring they keep up with their regular coursework so they remain well-rounded. As powerful as RLHF is, it is not a silver bullet. It's the first major step, but it comes with serious limitations that define the cutting edge of AI safety research today. First, as we've noted, it's incredibly resource-intensive. It relies on a human-in-the-loop system, but that loop is a bottleneck. We can build bigger models far faster than we can generate the high-quality human data needed to align them. Second, and perhaps most critically, is the problem of bias. The AI is being aligned to the preferences of a few hundred to a few thousand labelers. This group cannot represent the full diversity of global cultures, values, and perspectives. If you ask about a beautiful home, whose definition of beauty does it use? If you ask about a fair political policy, whose definition of fairness gets encoded? This is a profound societal challenge. Third, there is the risk of reward hacking. The AI's goal is simply to maximize its score from the reward model. It might discover that it can trick the judge. For instance, it might learn that long, confident-sounding answers get high scores, so it generates verbose, jargon-filled text that seems impressive but is actually vague and unhelpful. It's optimizing for the appearance of being good, not the reality. Because of these challenges, researchers are actively developing what comes next. This includes concepts like constitutional AI, where an AI critiques and improves its own answers based on a written constitution of ethical principles, reducing the need for constant human oversight. Other methods involve using AI models to debate each other to find flaws in reasoning, creating a more robust alignment signal than any single human could provide. The holy grail is to discover an alignment technique that scales with a model's intelligence, ensuring that as AI becomes ever more powerful, our ability to wisely steer it grows right alongside it. And for those who want to dive into the practical side, the complete code for this project is available on our GitHub page. You can access the link in the description of this video. Today, we are going to explore one of the most recent and powerful alignment algorithms, ORPO. The complexity of RLHF led researchers to ask, can we achieve the same goal more directly? This led to the breakthrough of direct preference optimization. The complexity of RLHF led researchers to ask, can we achieve the same goal more directly? This led to the breakthrough of direct policy optimization, or DPO. The core idea of DPO is brilliant. It showed that the entire complex RLHF pipeline can be mathematically simplified down to a simple loss function. All you need is a preference dataset with triplets of a prompt, a chosen response that is preferred, and a rejected response that is not. The DPO loss function then directly optimizes the model to assign a higher probability to the chosen response and a lower probability to the rejected response for the same prompt. This is much more stable and simpler than RLHF. However, DPO still has one drawback. During training, it needs to constantly compare the fine-tuned model's probabilities to the probabilities assigned by a frozen reference copy of the original model. This reference model consumes a significant amount of extra GPU memory. This brings us to the cutting-edge algorithm we'll be using today, ORPO, which stands for Monolithic Preference Optimization. ORPO's big idea is to ask, what if we could combine the simple SFT objective of learning to say the right thing with the DPO objective of learning to prefer the right thing into a single, elegant loss function? And that's exactly what it does. The ORPO loss has two parts. The first part is the standard next token prediction loss on the chosen response, just like in SFT. But it adds a penalty term. If the model assigns a very low probability to the good chosen response, it gets a large penalty. This forces the model to first learn to generate the good response well. Then, the DPO-like part of the loss kicks in to push the probability of the chosen response even higher than that of the rejected response. The incredible result of this combined approach is that it eliminates the need for a separate reference model. Because we're simultaneously reinforcing the correct language and the preference, the model doesn't drift away from its core knowledge. This makes ORPO even simpler and more memory efficient than DPO. It's the state of the art, and it's what we are going to build. So, you want to run the ORPO Llama fine-tuner project but don't have a powerful local GPU? No problem. We'll get it running in minutes using Google Colab. First, let's make sure our environment has the necessary hardware. Go to Runtime, select Change Runtime Type, and in the Hardware Accelerator drop-down, choose the T4 GPU. This is the key step that gives us the power needed for fine-tuning. Click Save. Now, let's bring in the code. In the first cell, we'll use the !git clone command, followed by the project's GitHub URL. When you run this, Colab will download the entire ORPO Llama Fine-Tuner repository into our workspace. Next, we need to navigate into the project folder that was just created. We'll use the command %cd orpo-llama-fine-tuner. The %cd command changes our current directory so we can run the project's scripts. Finally, you're ready to start the fine-tuning. Simply run the command !python main.py. Colab will now execute the main script using the free T4 GPU to handle the intensive training process, and that's it. You're now successfully running the ORPO Llama Fine-Tuner project in the cloud. We will walk you through the process of setting up access to our dataset and model. The first step is to create a new Google Cloud project and configure an OAuth client. On the screen, you'll see a Google Drive access page. If you're trying to access to dataset or model, you might encounter this page requesting access. Simply enter a message if you like and click Request Access. We will then approve your request. Meanwhile, to get started with the necessary credentials, open your Google Cloud console. If you don't have a project yet, you'll need to create one. Click on New Project and fill in the details. Once your project is created, navigate to the Client section. If you see a message that says Google Auth Platform not configured, don't worry. Click on Create OAuth Client. This will take you to the setup process for your credentials. This is a crucial step for authenticating your application's access to Google Cloud services. This process ensures secure access and management of your data and models. By following these steps, you'll have the foundational setup needed to move on to the next phase of our tutorial. Continuing from our last step, we are now ready to create the OAuth client ID that will be used to access our dataset and model. In your Google Cloud Console, under the Clients section, click on Create OAuth Client ID. You will be presented with a form. Select Web Application. As the application type, give your client a name. Something like Model Access is a good example. You don't need to fill in the authorized JavaScript origins or authorized redirect URIs for this particular setup. Click Create. Google will then generate your OAuth client credentials. A pop-up window will appear showing your client ID and client secret. This is your authentication key. Now, let's look at the file structure on the right side of the screen. You should have a folder for your project, in this case, ORPO Llama Fine-Tuner. Inside, you'll see files like config.py, main.py, and trainer.py. To properly configure your access, you need to create a file named credentials.json. Take the JSON snippet that Google provided and save it as credentials.json inside your project folder. The arrows on the screen show the file being renamed to credentials.json and being placed in the root of your project folder. This file will be read by your application to authenticate with Google Cloud Services, allowing you to seamlessly access your dataset and model for your fine-tuning tasks. This finalizes the setup for authenticated access. All right, with that deep dive into the theory, let's open up the code and start building. We're in the model/llama.py file. This single file will contain our entire from-scratch implementation of the Llama model architecture. First, let's walk through the imports at the top so we know what tools we have at our disposal. Import math. This is a standard Python library we'll need for just one thing, a square root calculation inside our attention mechanism from data classes import data class. This is a modern Python feature that gives us a super clean way to create classes that are primarily used for storing data, like our model configuration, from typing import optional, tuple. These are for type hinting. They don't change how the code runs, but they make it much more readable for us and other developers by specifying what kind of data to expect. Import torch, import torch.nn as nn, and from torch.nn import functional as f. These are our workhorses. We're importing the main PyTorch library, its core neural network module class which will inherit from, and the library of common functions like softmax and silu, which we'll use by the conventional alias f. With our tools imported, we define our model args data class. Think of this as the blueprint or the recipe for our Llama model. It holds all the key architectural parameters in one organized place. Dim is the core dimensionality of our model's embeddings. Layers defines how deep our transformer will be. Heads is the number of attention heads. Cave heads is a key parameter for an optimization called grouped query attention, which we'll explore in detail. Vocab size defines how many unique tokens our model understands, and norm EPS is a tiny number we'll add during normalization to prevent any division by zero errors. This data class is our single source of truth for the model's architecture. The first component of our Llama model is its normalization layer. Instead of the standard layer norm used in the original transformer, Llama uses a simpler and more efficient variant called RMSNorm, or root mean square normalization. Let's look at the init method. The key thing you'll notice is that it only has one trainable parameter, self.weight. This gain vector allows the layer to scale the normalized output. Unlike layer norm, there is no bias or shift parameter, which is part of what makes it simpler. The core logic is in the norm function. The formula for RMSNorm is to take the input vector x and divide it by the square root of the mean of the squares of its elements. The x.pow of 2.mean over minus 1 keep dim equals true part calculates the mean of the squares. Torch.rsqrt is a highly optimized function that calculates 1 over the square root, which is faster than doing torch.sqrt and then a division. The small eps value is added for numerical stability to prevent division by 0. In the forward pass, we first normalize the input x by calling our underscore norm function. Then, we take this normalized output and multiply it by our learned weight parameter. This allows the network to learn the appropriate scale for the features at that point in the model. It's a simple, fast, and effective normalization technique. Next, we come to one of the most important and clever innovations in modern transformers: how we handle positional information. The original transformer added a separate, learned positional embedding to the token embedding. Llama uses a more advanced technique called rotary positional embeddings, or ROPE. The core intuition behind ROPE is that instead of adding position information, we can rotate our query and key vectors in a way that encodes their absolute and relative positions. The amount of rotation depends on the token's position in the sequence. Because the dot product between two rotated vectors depends on the difference in their rotation angles, the attention mechanism naturally learns to favor tokens with a certain relative distance. Let's look at the code. The pre-compute effects CS function does exactly what its name says. It pre-calculates the cosine and sine components of all the rotation angles we will ever need, up to our max sequence length. It first calculates a set of base frequencies that are different for each dimension of our vectors. Then, it uses torch outer to create a matrix where each row corresponds to a position in the sequence and each column corresponds to a feature dimension containing the precise angle for that position dimension pair. The apply rotary MB function then takes our query and key vectors, xq and xk, and applies these rotations. The math looks a bit complex, but it's just a 2D rotation formula. It treats each pair of features in our vectors as a single complex number and multiplies it by the pre-computed rotation angle. This elegant method has been shown to be incredibly effective at helping transformers understand the relative positions of tokens. Another major innovation in the Llama architecture is an optimization called Grouped Query Attention, or GQA. Let's first understand the problem it solves. During inference, when the model generates text token by token, it stores the calculated keys and values from all previous tokens in a key value cache to avoid recomputing them. In standard multi-head attention, you have a separate key and value head for every query head. This cache can become a huge memory bottleneck. To solve this, a technique called multi-query attention was proposed, where you have many query heads but only a single key and value head that is shared by everyone. This drastically reduces the size of the KV cache but can sometimes lead to a loss in quality. Grouped query attention is the perfect compromise. We have our full number of query heads, but we have a smaller, intermediate number of key and value heads. These KV heads are then shared across groups of query heads. For example, we might have 32 query heads, but only 8 KV heads, where each KV head is shared by a group of 4 query heads. The repeat KV function is the simple but essential mechanism that implements this sharing. It takes the key or value tensor, which has the smaller number of n KV heads, and it skillfully expands and reshapes it to match the full number of query heads. This effectively copies the KV heads so that each group of query heads can attend to its designated shared key and value. Alright, let's assemble all these advanced components into our main attention module. In the init method, we first calculate all our head dimensions based on the model args. We define our 4 crucial linear layers, WQ, WK, and WV, to project the input into query, key, and value vectors, and WO for the final output projection. Then we have a very important check. We see if our PyTorch version has scaled dot product attention. This is the function for flash attention, a highly optimized implementation of the attention mechanism that is much faster and more memory efficient. If it's not available, we fall back to creating a manual causal attention mask. Now for the forward pass, let's trace the data flow. The input X comes in. First, we pass it through our WQ, WK, and WV layers, and then reshape the output to separate the heads. Notice XK and XV are reshaped with the smaller n local KV heads. Next, we apply our rotary positional embeddings to the query and key vectors, rotating them to inject the positional information. Then, we call our repeat KV function to implement grouped query attention, expanding the key and value tensors to match the number of query heads. After transposing the tensors to prepare for matrix multiplication, we finally calculate the attention. If flash attention is available, we use the single, highly optimized scale dot product attention function, simply setting is causal equals true. If not, we perform the manual attention calculation. Matrix multiply, Q and K transposed, scale, add the mask, apply softmax, and multiply by V. Finally, we reshape the output tensor back and pass it through our final output projection layer, WO, to get the result of this attention block. Every transformer block has two main components, an attention sublayer and a feed-forward sublayer. We've just built our advanced attention module, now let's build the feed-forward part. The Llama architecture uses a specific variant of a feed-forward network called SWI-glue. In the feed-forward class, you'll notice it has three weight matrices, W1, W2, and W3. The forward method implements the SWI-glue formula. The input X is projected up by two separate matrices, W1 and W3. The output of the W1 projection is passed through a SILU activation function, which is then multiplied element-wise with the output of the W3 projection. This result is then projected back down by the W2 matrix. This gated structure has been shown to be very effective. Now we can finally assemble our complete transformer block. In its init, it simply creates an instance of our attention module and our feed-forward module. It also creates two separate RMSNorm layers, one for each sublayer. The forward pass clearly shows the modern pre-normalization structure. The input X is first normalized by attention norm before it goes into the attention module. The output of the attention is then added back to the original unnormalized X in a residual connection. This result, H, is then normalized again by FFNorm before it goes into the feed-forward network. And finally, that output is added back to H in a second residual connection. This norm, then transform, then add pattern is a key feature of the Llama architecture and is critical for stable training of very deep networks. We've built all the components and now it's time for the final assembly in our Llama class. In the init method, we put all the pieces together. We create our TOC embeddings layer, which will map our input token IDs to dense vectors. We then create our stack of transformer blocks, using a module list to hold all n layers of them. After the blocks, we have our final norm layer and the output linear layer that will produce our final vocabulary scores, or logits. Finally, we call our precompute freq CIS function one time to calculate our rope frequencies, and we register them as non-persistent buffers. This is a small optimization that tells PyTorch these tensors are part of the model's state, but don't need to be saved in the state direct, as they can always be recomputed. Now for the forward pass. It takes our input tokens and optional targets. First, it gets the token embeddings. Then, it slices our pre-computed ρPE frequencies to match the current sequence length. It then passes the embeddings through every single transformer block in a for loop. After the final block, it applies the final normalization. Now we have a conditional check. If targets are provided, it means we are in training mode. We calculate the logits for the entire sequence. We then perform a crucial shift. We shift the logits one position to the left and the targets one position to the right. This aligns the prediction at time step t with the target at time step t plus 1, which is exactly the next token prediction task. We then calculate the cross-entropy loss. If targets are not provided, it means we are in inference mode. We don't need to compute logits for the whole sequence. We only care about predicting the next token. So as an optimization, we only compute the output for the very last token in the sequence, which is much faster. Let's take a quick look at config.py. This is our project's control panel. We've defined all our important parameters here. This includes training parameters like the batch size, epochs, and learning rate. A key parameter for our specific fine-tuning task is alpha ORPO. This is the scaling coefficient, often called lambda, that balances the two parts of the ORPO loss function, the standard language modeling loss and the preference ranking loss. The value of this parameter can have a significant impact on the final performance of our fine-tuned model. We also have our system and path configurations, which tell the script where to find the tokenizer, where to save checkpoints, and which dataset to use from the Hugging Face hub. Having all of these settings in one place makes our code much cleaner and our experiments much easier to manage. Our project is designed to start from a pre-trained model, which we need to download. The script utils/gdrive.py is a self-contained utility for handling this. The getDrive service function is responsible for authenticating with the Google Drive API. It uses the standard OAuth2 flow. The first time you run it, it will look for a credentials.json file, which you need to get from the Google Cloud Console. It will then prompt you to visit a URL in your browser, authorize the application, and paste back an authorization code. Upon success, it saves your credentials in a token.json file. On all subsequent runs, it will find this token.json file and reuse your credentials without asking you to authorize again. The download and extract zip function then uses this authenticated service to download the specified file from Google Drive. It downloads the file into an in-memory buffer, shows the download progress, and then uses Python's zip file library to extract the contents, our model and tokenizer, into the correct directory. This makes the initial setup of our project completely automated. Now we arrive at the main conductor of our project, the ORPO trainer class in trainer.py. This class encapsulates all the logic for our fine-tuning process, making our main script incredibly clean and simple. Let's look at the init method. It acts as a master setup function. Instead of having one giant, messy constructor, we've broken down the setup process into a series of logical private helper methods. It first sets up our weights and biases logging, then it sets up the tokenizer, then it loads and prepares our llama model, then it prepares our data loaders, and finally, it sets up our optimizer and learning rate scheduler. We're going to walk through each of these setup methods one by one to see exactly what they do. Let's look at the setup methods inside our ORPO trainer. First, setup port tokenizer calls our Google Drive download utility to ensure the files are present. Then it uses auto-tokenizer from pre-trained to load our tokenizer from the local path. It then configures the tokenizer with the specific chat template and pad token that the model expects. Next, setup model is where we load our pre-trained weights. It loads the base.pt checkpoint file, which contains both the model's configuration and its weights. It intelligently uses the model config from the checkpoint to create an instance of our from-scratch Llama class with the exact same architecture. Then it calls model.loadStateDictionary CKPT to load the pre-trained weights into our model. This is a perfect example of how to separate a model's architecture from its trained weights. Finally, here prepare data loaders handles our dataset. It's a smart function that first checks if we have a pre-processed tokenized version of the dataset saved locally in a cache. If so, it loads it instantly. If not, it downloads the raw dataset from the Hugging Face hub, performs all the necessary filtering and pre-processing steps to get it into the format we need for ORPO, and then saves the result to the cache directory, so we never have to do this slow pre-processing step again. It then creates and returns our standard PyTorch data loaders for training and validation. Now for the mathematical core of our trainer. The setup optimizer function creates our AtomW optimizer, which will update our model's weights. We also define a custom learning rate scheduler. This scheduler will implement a warm-up phase, where the learning rate gradually increases from 0, followed by a cosine decay phase, where it smoothly decreases. This is a very common and effective schedule for training transformers. The calculate log probs function is a complex but necessary helper. Its job is to calculate the total log probability of just the response part of a sequence, ignoring the prompt part. It does this with some clever masking. Finally, the get ORPO loss function. This is the heart of the entire project. It takes a batch of data and first performs a forward pass with the positive input IDs to get loss pos, which is our standard SFT language modeling loss on the chosen response. It then uses our helper function to get the log probability of this chosen response. It does the same for the negative input IDs to get the log probability of the rejected response. It then calculates the log odds term. This formula, taken directly from the ORPO paper, represents the odds ratio between the chosen and rejected responses. This term is then passed through a log sigmoid function. The final total loss is the combination we discussed in our theory section. It's the standard SFT loss, loss pos, minus our preference loss term, scaled by alpha ORPO. This is the single value we will backpropagate to train our model. With all of our setup methods and our loss function defined, the final train method is the orchestrator that puts them all into action. It starts by printing a banner and getting an initial estimate of the loss before any training has happened. This gives us a good baseline. Then it enters the main for loop, which iterates over our desired number of epochs. Inside this, we have another loop that iterates through every single batch in our train loader, wrapped in TQDM to give us a nice progress bar. For each batch, we perform the standard PyTorch training steps. We call optimizer.0grad to reset the gradients from the previous step. We move the batch of data to our target device, like the GPU. We call our getORPOLoss function to perform the forward pass and compute our final loss for this batch. This is the learning step. Total loss.backward computes the gradients. ClipGrad.norm is a standard technique to prevent gradients from exploding. And optimizer.step and scheduler. Step, update our model's weights and the learning rate, respectively. Periodically, based on our log interval, we pause to call our estimate loss function, which evaluates the model on both the training and validation sets, and we log these metrics to the console and to weights and biases. Finally, at the end of every epoch, we call save-checkpoint to save our model's progress. The entire loop is wrapped in a try. Finally blocked to ensure that even if we interrupt the training, our resources are cleaned up properly. Last but not least, let's look at main.py. After all the complexity we've built in our model and trainer files, our main entry point is beautifully simple. This is a sign of a well-designed modular codebase. At the top, we have a place for you to insert your Hugging Face API token. We also enable some PyTorch performance enhancements like allow TF32, which can speed up computation on modern NVIDIA GPUs. Then we import our ORPO-trainer class. The main function itself is incredibly concise. It does just two things. First, it creates an instance of our ORPO-trainer. As we know, the __init method of this class will trigger our entire setup process, downloading data, loading the model, and preparing the optimizer. Second, it calls trainer.train, which kicks off the main training loop we just reviewed. The standard main block ensures that this main function is called when we run the script from our terminal with the command python main.py. That's it. All of our complex logic is neatly encapsulated in our trainer, and our main script is just a clean, simple launcher. And with that, our training process is complete. Let's take a moment to step back and appreciate the incredible state-of-the-art system that you have just built. This was a true deep dive, and you've accomplished a tremendous amount. We started our journey with a deep dive into the theory of AI alignment, tracing the evolution of fine-tuning from the early days of supervised fine-tuning through the complexities of RLHF and all the way to the modern and efficient DPO and ORPO algorithms. Then, we rolled up our sleeves and did what very few tutorials do. We built a complete LLaMA model from absolute scratch. You implemented every single advanced component from RMSNorm and rotary positional embeddings to grouped query attention, giving you a fundamental understanding of this powerful architecture. finally we brought it all together. We created a professional end-to-end training pipeline that automatically downloads our data and pre-trained model. And we successfully fine-tuned our from-scratch llama using the elegant and powerful ORPO loss function. You now have a deep practical understanding of how modern language models are built and aligned. The learning doesn't have to stop here. I highly encourage you to take this project and make it your own. Go into the config.py file and experiment with the hyperparameters. See for yourself how changing the alpha ORPO value affects the model's final performance. Try finding a new preference dataset on the Hugging Face Hub and fine-tune this model to be a specialist in a domain you're passionate about. And for a fantastic next step, you could build an Inference, PyScript, and a Gradio web interface to easily chat with and showcase your newly fine-tuned model. If you've enjoyed this deep dive masterclass and you feel like you've leveled up your AI engineering skills, it would mean the world to me if you could take a second to like this video and subscribe to the channel. Your support is what allows me to create more free, in-depth tutorials just like this one, and it lets me know that this content is valuable to you. Also, be sure to share it with any friends or colleagues who you think would find it useful. Thank you so much for joining me on this incredible journey. Happy coding, and I'll see you in the next video.